Picture this. A user transfers $1,000 out of their account. It's a high-stakes moment, right? But a millisecond later, their mobile app refreshes, and that $1,000 is still just sitting there. Thinking the transfer completely failed, they panic. So, what do? They click send again. Well, guess what? You just double-charged them, you overdrew their accounts, and you completely ruined their day. So why did this disaster actually happen? It happened because of a fundamental misunderstanding of how DynamoDB replicates data under the hood. Your application just got hit by a stale read. In this explainer, we're going to dive right into exactly how DynamoDB consistency works in distributed systems. We'll unpack the exact reason why your database occasionally lies to you. Because, let's be real, it's not magic, it's architecture.
To really understand this, we have to look at the baseline mechanics. When you write a piece of data to DynamoDB, it doesn't just save it to a single hard drive and call it a day. To guarantee extreme durability, DynamoDB synchronously replicates your data across 3 physically isolated availability zones within an AWS region. Let's walk through how this process actually works. When your application executes a put item or update item request, DynamoDB first writes that data to the primary storage node. Next, it sends the data out to the secondary nodes. And as soon as a majority of those nodes acknowledge the write, DynamoDB tells your application, success. Your code moves on, thinking everything is fully complete and locked in.
But here is the catch. There is a tiny microsecond gap before that data fully propagates to the final node in the cluster. It's an almost imperceptible window of time. But in a high-traffic application, that tiny window is a massive hole. When you go to read that data back, AWS gives you a massive architectural choice. You are basically choosing between pure speed and absolute accuracy. Let's break these two down. By default, DynamoDB performs what's called an eventually consistent read. With this type of read, DynamoDB routes your request to a randomly selected storage node. Now, this is incredibly fast and highly efficient, but if the system happens to query that one secondary node that hasn't received the latest update yet, it's going to hand you the old, stale version of the data. Now, on the flip side, if your application absolutely cannot tolerate stale data, like our bank transfer example earlier, you have to explicitly configure your API call to perform a strongly consistent read. When you do this, DynamoDB forces the read to verify the latest state across all the nodes. It guarantees that you will receive the most up-to-date data, reflecting all successful prior write operations. It's perfectly accurate. So you might be wondering, why wouldn't you just use strongly consistent reads for absolutely everything? I mean, it sounds like the safest bet, right? Well, it really comes down to 2 major trade-offs: cost and scalability. Let's talk about the cost first. In DynamoDB, throughput is billed in read capacity units, or RCUs. One RCU gives you exactly 1 strongly consistent read per second for an item up to 4 kilobytes. But that exact same RCU will give you 2 eventually consistent reads. It's literally a 2-for-1 deal. If you default your entire application to strong consistency just because you're playing it safe, you are instantly doubling your AWS database bill. Let that financial impact sink in for a moment. Now, let's talk about scalability. This is the famous CAP theorem in action in the real world. If there's a network blip or an availability zone outage, a strongly consistent read might not be able to securely verify the latest state across the cluster. And instead of risking giving you old data, DynamoDB will just throw an HTTP 500 server error and fail. Your application literally goes down. An eventually consistent read, however, handles that exact same network blip gracefully. It will still succeed by giving you whatever data it has currently available. By accepting eventual consistency, you are trading a tiny bit of accuracy for massive bulletproof availability. Think about that for a second. If your AWS Lambda function processes an e-commerce order and instantly tries to read the user's updated profile to generate an email receipt, well, an eventually consistent read might pull the pre-order state. Your receipt will show the wrong data, and you're going to confuse the customer. For immediate read-after-write flows within the same function, you absolutely must enable strong consistency. But on the other hand, if you're just loading a social media feed or a product catalog, nobody cares if a comment or a review takes 200 extra milliseconds to show up. Use eventual consistency and save those RCUs. Section 1, Exam and Production Traps. This is where developers fail on the DVA-C02 exam, and much more importantly, in the real world. Here's a classic mistake. A team builds a global secondary index, or GSI, to query their data in a totally new way. They test it out, they realize their data is occasionally stale, so they update their code to request a strongly consistent read against the GSI, and the code instantly breaks. Why? Because a global secondary index is effectively a shadow table. When you write to the base table, DynamoDB updates the GSI asynchronously in the background. Because of this structural, architectural decoupling, you simply cannot perform a strongly consistent read on a GSI. It is physically impossible. GSIs only support eventual consistency, period. Now, imagine this scenario. You have a massive global application spanning across New York and London. You smartly use DynamoDB global tables to keep the data synced across continents. A user updates their profile in New York, and a Lambda function in London reads that profile a split second later. The data is old. So, why did that happen? It happened because global tables use storage-based asynchronous replication across AWS regions. While it typically syncs in well under a second, there is a hard rule you absolutely need to memorize. Cross-region strong consistency does not exist. You only get strong consistency within the local region.
Finally, as your smart friend trying to save you from a massive architectural failure, I have to warn you about the DAX trap. DynamoDB Accelerator, or DAX, is a brilliant in-memory cache designed to give you microsecond read performance. But if you execute a strongly consistent read through a DAX cluster, DAX is forced to completely bypass the cache and hit the underlying DynamoDB table directly to guarantee accuracy. If you're relying on DAX to magically lower your latency, but you force strong consistency on every single read out of fear, you are completely defeating the purpose of the cache.
All right, let's lock this down and summarize. Here are 3 rapid takeaways to remember. Number 1, eventual consistency is a DynamoDB default. It's twice as cheap and highly available, but it can return stale data due to microsecond replication lag. Number 2, strongly consistent reads guarantee you get the absolute latest data, but they consume double the read capacity units and can actually fail during network disruptions. And number 3, global secondary indexes and cross-region global tables update asynchronously and exclusively support eventually consistent reads. One final warning before we wrap up. Never default to strong consistency just because you're scared of stale data. If you design your application to tolerate eventual consistency wherever possible, your system will be infinitely more scalable, resilient, and cost-effective. So the next time you build a feature, ask yourself, is absolute perfection really worth taking your entire system offline?